My name is Dr. Dominique McCowan. I'm going to be talking to you about coral ecology and management. This is Module 1 of a 5-week course. We're going to go over the ancient history and evolution of coral reefs. Depicted there is a Devonian reef, about 390 million years old. The modern precursors to modern corals. We'll talk about the ancient ecology and how it moves forward into current stuff. So overall, the presentation aim is to explore the rich evolutionary, ecologic, and geologic histories of corals, reefs, and coral reefs. We're going to go over some main concepts, kind of keep in your head. First of which is that there's a coevolution with all these different factors, the physical, chemical, biological, and geology through time. Next is that there's intermediate disturbances have an important effect on biodiversity on both ecological and evolutionary levels. The next one is the enigma of coral resilience and susceptibility that can be differentiated by a matter of time. Then we're going to look at cryptoevolution and scleractinian coral ecology. And we'll finish up looking at how different fossils and molecular evidence is put together, get an idea for how that field has worked. We're also going to do this video in 3 segments, about 20 minutes each, so just prepared for sections of it. Okay, so we'll start with the evolution of life on Earth. This is a really broad overview. We'll kind of dig in broad and then go smaller as we go. So from this, on the bottom left-hand side, you can see the elemental table there. From the Big Bang, hydrogen, helium was formed, and then everything compounded upon that. So we have everything from astronomy down to biology, and even at the branches of that into genetics and stuff on that lines. On the left-hand side there, you see some of the transformations of Earth through time. The red is the Hadean-like environment. Purple Earth is a biosignature they're looking for. Potentially happened when in competition with chlorophyll, retinol, and another pigment, antennae. Likely put off that purple from red and blue wavelength absorption compared to the chlorophyll that we know of now, absorbing green. And then you got just modern Earth and how just varied it's been in its history. We're going to go over a little bit of the geology and the paleo this course, this module I should say, and then move on forward. So again, this idea that all these different factors are interacting at the same time through history to impact everything else. The entire study of ecology is the interaction of all these different things. So you can see here there's always cycles going on. These different basic constituents are moved throughout the environment, be it in the atmosphere all the way to the rock, bedrock, and into the sea a lot too. But there's always an interplay between these carbon sinks and these carbon sources. And sinks are a way that it can be stored in the earth or in the air, and the sources are what kind of takes them out of it. So we have that, and then it's important to think on deep time in regards to coral reefs. This is a pretty basic geologic time scale. You have on the right-hand side, the oldest, lower right-hand corner is the oldest bit there. Again, the Hadean into Archean, Proterozoic, and then it moves forward into the green and on back. Each of those lines and eras and everything like that is demarcated due to different disturbances, and the assemblage changes in each one of those. So it's kind of immediately apparent there's been a very fluid history to Earth where the assemblage changes have happened quite often. And we'll get into more of that as this lecture goes on. There's 3 major fields of kind of viewing this deep time. One's the idea of catastrophism, where there's these huge events that cause mass extinctions and have huge impacts on the Earth. The next idea is the idea of gradualism, This was the common idea when Darwin created, didn't create, when he coined, I guess, evolution by natural selection. It's the idea of gradualism, is nice and slow stuff happening. It was catastrophism before that, and they kind of almost disregarded catastrophism and went towards gradualism, and in reality we find both of those happen. And then there's uniformitarianism, and this is the idea that all processes acting today have taken the same rate to occur through time, which is also not entirely true with that one as well. Processes have variable times relative to where they're occurring and what the environmental conditions are locally. So how do we know these things anyway? We're going to go through a lot of the evolutionary history on Earth, and it's what evidence are we compiling to produce that. There are fossils. Lagerstätte is a word that means just very well preserved kind of thing. These Lagerstätten tend to be Ediacaran into Precambrian, Cambrian era, very old, 550 million to about 460 million, around there. So we have biostratigraphy. The Lagerstätte are just very well preserved ancient fossils, generally soft-bodied, soft tissue even. Then we have biostratigraphy, which is the idea of rock shifting and being able to tell age from how the rocks are shifted. And not only how the rocks are shifted, but what fossils are in them and if you can relative date them. Then, of course, that brings us to the radiometric and relative dating. So looking at the half-lives of chemicals and then also comparing index fossils to different areas of that. Then we can also look at continental drift and plate tectonics. The idea here, important to where I'm from, around Louisville, Kentucky, we have an ancient marine environment here, an ancient reef. And we know that because of the limestone, which is only formed in marine environments. But it's interesting that now we're in the middle of a temperate, breadbasket, and once upon a time we were tropical coral reef. So you see these also in continental drift, where you'll find fossils, like we have fossils similar to Australia here with the corals. So you can piece together where places used to be more connected and they're not anymore. This graph here on this side just shows some of those really good Lagerstätten. Again, the Ediacaran into the Cambrian, and we'll talk more about that specific time point. So how do we know the age of rocks and or fossils? As said, relative dating. The fossils of the Lagerstätte, so you have these really well preserved fossils. You can get a really good idea from the mud rocks how old they are, and you can use those to then relative date other stuff when you find that same organism in another assemblage. There's the idea of succession, where if you find one on top of another, it is older, generally. There's a couple of biostratigraphy rules that do outline that. And that is the original horizontality. The idea, if you have a fault or something that were to shift it, you could still tell which one is older. The same kind of principle with superposition, if it's overimposed on it or something. And then there's also cross-cutting relationships, where fossils will literally cross into a new one will cross into an older one. So there's a lot to be kind of teetered out between just finding a fossil assemblage. So locations in geomorphology, as mentioning Falls of the Ohio near Louisville, Kentucky, is the bottom of a reef that used to span from New York down to Kentucky. And then it's similar in size to the Great Barrier Reef of today. It was this ancient reef of about 390 million years ago. So we have that, and then moving forward onto numerical dating, the radiometric dating, for instance, carbon dating, is by the elemental half-lives of minerals. Igneous rock does better. It's fire formed, and you can tell a lot older stuff per se than just carbon dating. There's also the correlation of relative dating with index fossils. So the index fossils mentioned above But you date those, and then you can date other areas as well based on those relative index fossils. And there's also magnetostratigraphy. The idea right at the seafloor spreading spots, that's a tricky one, there's iron deposited, and whatever way it shifted with the magnetic poles allows you some orientation and age to that as well. So this is just the study of taphonomy, which is how fossils are made pretty much, and how it's preserved. This is just an example of a crocodile dying in a river, sediment slowly covering up the body, the tissues kind of dissolving away and leaving the skeleton, and then that skeleton getting embedded in the rock. This is the principle behind the fossil fuel formation. Most of what we use for oils is from little plankton that fill the spaces and release this nice gas that we use for energy. So these ideas, the relative and absolute dating, the relative again being the index fossil, where if you know its age, you can compare it to other things, and then also you have the half-lives of certain chemicals. What's interesting is the uniformitarian view that those half-lives are going to be fairly consistent is unknown if the environmental conditions were rapidly changing. So it makes it kind of hard, you'll notice later, to pinpoint exact time frames that it took mass extinctions to occur, and these major disturbances is that we're not sure if the rates were the same. So this is kind of showing the biostratigraphy, how you can get placements of these, the idea that transitional forms aren't often actually preserved in the fossil record. There's a lot of rules to fossils, and most times they're in sedimentary rocks, which are in basically it's a shallow water that gets transformed into time, and it makes a really nice spot for fossils to form. That's the primary spot for them. So here are some of the index fossils through time. A lot of marine life, a lot of different stuff, especially reef life. That they become so abundant, they're just a really good fossil to use. For instance, the trilobites have something like over 30,000 different species, and they're very indicative of their time frame based on the certain adaptations they have at that time. And then the idea of the magnetostratigraphy here, this is just showing some of the reversals and normal polarities. These happen generally about every 10,000 years. There's 10,000 years. There's a polar switch, and it's recorded in the seafloors. But that helps time stuff as well. And then we'll look at environmental geology and paleobiology and take a hold until the next video. So we'll look at what environmental geology and paleobiology helps us learn is by looking at these fossil assemblage structures, what animals lived, when, what adaptations they have, we can understand their environment more. Again, the continental drift and which parts were connected. If you look at the manner of taphonomy, how the fossils were formed, and the minerals involved, it can tell you a lot about the environmental conditions at the time. For example, till represents glaciation. Desert rocks are often red from oxidation, and limestone, as mentioned, represents a marine environment. Mud rocks, those formed in environmental conditions like sedimentary, around the world are used to determine global paleoceanic O2 levels. Really good to let you know how much oxygen was around. Color does a lot to tell you that too. So the growth bands in live and fossilized trees and corals, as well as glacial ice cores and rock formation cores, help identify environmental changes. Still used to this day. For instance, the mud rocks above would have been a darker, blacker color when more oxygen deprived and more carbon life has died and is involved in the formation of the rocks. So thinking coal and stuff like that is also very abundant fossil-wise.